by email.
No, I don't know. Maybe he just doesn't want you to read it, I guess. It used to be like that, right? Recommendation letters kind of.
Yeah, never seen by the candidate.
No, exactly.
Exactly. It's just for KTH. They
Yeah.
ask you to upload it yourself.
Which is kind of strange, right?
Yeah,
It's just really stupid.
it's really tricky.
But it's always heartwarming to read what they write about you.
Yeah, of course.
I mean,
If
hopefully.
Yeah, so. That's interesting.
Just get things straight.
But I'm not going to use masters for KTH, so I don't really have to.
I'm going to start casting. Yeah, I'll do this and I'll start casting you about the next.
Just Mirella and Steve.
So what would you rather? Socks or
Yeah. I asked for two and they said no.
no, make sure you buy it.
Yeah, but I mean, it's a bit tricky if he doesn't want you to do it.
Then it's a risk.
I'll be fully dependent on these.
Yeah, exactly.
But otherwise you could use Stefan.
By yourself.
But then Matters knows more about get work, I guess.
All right. So, welcome to Monday. Here we are in another week. I think I kind of need to stay sitting down if I'm going to keep my mask off, which seems a better way to lecture. So you won't have me like dancing around like I usually do. Also, I forgot the really snazzy connector that I needed to connect the webcam, so we're back to just having my Mac recording as best it can. Sorry, live thing. All right, so quick check-in. How are things going? How's your week looking? How are you feeling about the course and other things? Any issues I need to be aware of? Quiz went okay? Awesome. All right, so just to clarify, so next week is midterm week. Midterm will happen at whatever time it was that I put on Canvas, in place of the Thursday tutorial. So if you would usually have your Thursday tutorial later, then you don't have it. You just have the midterm and then go and crash or do whatever it is that you do after a midterm. In terms of midterm content, it will be up to and including everything we get to by the end of today's lecture. So I will post that specifically afterwards. I'm not expecting you to learn stuff that we don't do in the lectures for a midterm, obviously. Okay. I will put up the usual online quiz for this week's material, and then I will also put together one or two kind of practice midterms to give you a flavor. If you're wanting a sort of idea, I mean, I will take a variety of questions of the textbook type and also of the web work type. But obviously you get to do full working, so you don't, yeah. Any thoughts around the midterm? Concerns?
Do we get to use a graphical display calculator? I know what its application is.
Yeah, but I mean, I'm going to ask you questions where that might not be super helpful. So my thinking when I set any kind of assessment is I just want to check that you really understand the work. I don't want to break you. I don't want to torture you. I just want to check that this whole knowledge acquisition process that we're going through is actually functioning. So the best way that you can kind of get ready for a midterm written by me is to think about, if you were a sane and sensible maths lecturer lecturing this course, what would you ask? Okay, there was a question.
It's in person, right?
Yes.
And what happens if we get symptoms or we get to retake it later or online? Is that a possibility?
Okay, not that. These are good questions. Let me ponder them deeply and get back to you. Okay. I think the best bet will be something like a reset the following week, or yeah. I think it's really important that it gets written in person so that you have a practice, because the final will be in person. Yeah. But let me just think through that. There was a thing here? No? Alright, let's do some maths.
Wait, so are there calculator restrictions?
No,
No?
no.
Okay.
I kind of feel like with calculators it's got to be all or none.
Yeah.
And I'm not going to make you do arithmetic if I can't do it. So, yeah.
Okay.
So I can just bring my graphical calculator.
Sure.
We're going to draw a line between like a computer and a calculator.
Hmm?
Where are we going to draw the line between a computer and a calculator?
That is also a good question. I mean, it's becoming so blurred now.
Whatever, upload the whole PDF of the book on my account.
Just anything without internet connection.
Even internet is just advanced arithmetic for calculators.
Alright. So, we are dealing with functions of many variables. And so far, so just to give you a flavor of what we're looking at, so far we've introduced the idea of derivatives, and we said, well, if you've got a surface, then when you start thinking about the slope, initially we just said, well, we'll think about the slope, for example, in the y direction with the x held constant, in the the x direction with the y held constant. There are many different tangent lines to a surface. And we started taking derivatives, and then the natural thing and we did some parameterization of things, and the thing that ends up happening is obviously we have to do the chain rule. You needed the chain rule back in calculus of one variable, now you really need the chain rule. Unfortunately, there isn't anything as nicely simple as the chain rule is in one variable. So let's just, to get you back thinking about chain rule, here's a function of one variable. Please find its derivative and tell me how you did it. All right, who's got it? Okay.
Oh, I came to minus 2x sine x squared plus 3.
Okay, so let me just write this down. You said the first derivative is minus 2x sine of x squared plus 3. Any advance on this? Disagreement on this? Okay, so what was your thinking? Or was it just muscle memory by now?
Reasonably muscle memory, but I
Okay.
just thought, okay, you've got the outer part of the chain,
Mm-hmm.
so the function, so to say.
So basically
gets
you've got your cos of
Yeah.
something.
cos of something, exactly. You differentiate the cos.
Okay, and that gave us
minus
our
sine.
minus sine of the something,
Yeah.
and then-
you get the something.
and then
just
you
nice.
differentiated
Yeah.
the something.
And then you multiply by the differentiated something.
Okay.
Exactly.
Awesome. Okay. So the idea being that we have a function within a function, or you can think of it as, I always forget this word, composition, function composition. So it's not enough to just take the derivative of the outside function, you have to take the inside function. And I'm sure you've gone many layers deep, you can have functions of functions of functions of functions. Okay. Now we add the wrinkle that we not only have functions of functions, we have many variables going, and if you think about it, every variable can be a function of a different variable. So suddenly we don't just have a kind of a single chain of things, we can have branching trees of craziness. Okay, so the trick when you're trying to differentiate a function of many variables, which you're going to chain rule, is you have to think about it. You can't just kind of go for it with a particular rule. You have to analyze your function a little bit and think about it. But that's not a problem. Okay, so so this is broken up. Here we've got a function z of x and y. And x and y are each a function of t. Okay, so if we were to write this properly, what we'd really have is z is equal to f of x of t, y of t. And one way to deal with this would be to just plug in your x of t and your y of t into your formula for f, and then just differentiate with respect to t. Okay, but you can also chain rule it. So the way that you would do this is, so what we're actually wanting, and I just see that I've got my notation, I was a bit messed up there. Okay, so really, z is just a function of t. So we can take the full derivative. So we can find dz by dt. But we need to go through the functions y and x. And the way that you do it for this particular version shouldn't really come as a surprise. If you just had z was equal to f of x and x was a function of t, you would have that bit there. But now we have that z is a function of x and y, so we have a second term here. Does that seem reasonable? All right, so using what we've just got here, write down what you think the And if you're finished, just to kind of convince yourself that this is the right way to be going, write z as a function of t. So plug in for x and y in here, and then differentiate that with respect to t, and check that you got the same thing as you got using the funky chain rule. All right, so let's talk through it. So if we're using this rule over here, it says first take the partial derivative of z with respect to x. So we have a look at this thing over here, and we say, okay, partial with respect to x, that's going to be a minus 2x minus y squared. Y squared is acting like a constant here, so that just differentiates to 0. Plus 4 is a constant, differentiates to 0. Okay, so that we've dealt with this bit, and now we have to multiply, so do our actual chain rule, where we've got our dx by dt, and dx by dt, that's going to be times 3t squared. Okay, and now we do plus the y bit. So we get dz by dy, so that's going to give us, a minus 2y, and we need the dy by dt, which will be minus sine of t. And we need to, did I do everything? I think I did everything. Yes. Okay. All right, so now if we write out z of t, that's going to be a minus x squared, so that's going to be minus t to the 6, and then we want minus y squared, that's going to be minus cosine squared of t plus 4. Let's take dz by dt straight off, so we've got a minus 6t to the 5 minus 2 cos t sine of t, and that's it.
Minus something.
Maybe? Did I do that wrong?
I mean, the
I could well have done it wrong.
differentiation of cos.
Oh,
the
yeah.
minus sign, so
Yeah,
it
no,
cancels
we
out.
should have a change. Yeah, okay. All right. Are these the same?
If you plug in x and y.
Right, so the only difference here is that we haven't substituted in for x and y. But if we do that, then we get our minus 6 t to the 5 plus 2 cos t sine t. Clearish? Sweet. So in a test or exam, either method works. I would recommend both from a checking perspective. But there will be times when, for example, we have more dependencies where substituting in to get your, so here we have z is a function of x and y, and it's all nice and straight, and x and y each depend on s and t. Okay, so if you plug everything in, z is a function of s and t. So now we would be first of all looking at partials with respect to s and partial with respect to t. And one thing you could just do is plug in whatever your x function is as a function of s and t, and whatever your y function is, and do the usual, or you can chain rule it, which should be starting to look somewhat familiar. Okay, show of hands. This is, I want to go on. Please don't make us do this in class. This is, maybe we should do this in class, and this is, we really need to do this in class. All right, we're just going to go through this in class. Okay.
Also wondering, can you also like mix it around? Because now we put it only in, like, we put both either an S or both either an T, right? With respect to the X and Y. Could you also pick like one X, take derivative with respect to T, and then take derivative of Y with respect to S? That's again like another type of derivative in Z.
I mean, yeah, that would be another kind of derivative.
Yeah, but like, is that anything sensible that we use as well, or do you not use
Well,
that?
I mean, if you think about it, in this context, x and y are just kind of intermediate variables. So if you're asking specifically for the derivative of z with respect to s, then you're going to want to take the derivatives of x and y with respect to s.
But is there any derivative with respect to like set that we would be interested in that like uses t for the x and y, s for the other, or is that maybe have to
I mean,
know
I think
context or something?
Offhand, I don't know,
No.
but I feel like most things are applicable somewhere.
Yeah,
That's a stretch goal. Go and think about
I'm
it.
just wondering, like, because it
Yeah.
wasn't written yet.
Yeah.
It's
No, but
still
usually-
possible,
No, usually you would you pick the thing you're differentiating with respect to, and
Yeah.
Yeah.
That makes the most sense.
all right. So what I would like is this half of the class. Please, would you find df by ds? Okay, your job is df by ds. Your job is df by dt. Go. All right. Team df by ds. please
2st to the power 4
2st to the power 4
plus 3.
plus 3. General consensus on team df by ds? Okay, so that seems like we don't need to go through that. Team df by dt?
4s squared times t cubed minus 3.
T cubed
No,
minus...
times 4s squared times
Sorry.
t cubed. Sorry.
That's me, I can't hear right now. T cubed
Minus 3.
minus 3. General agreement? Okay. And we could check that by just differentiating this as appropriate. All right. So the moral of the story is when you're you're dealing with multiple variables and you have parameterizations, slow right down, think through what you're doing. If in doubt, go and do a one variable chain rule to kind of get your mind thinking about how it all works and then unpack it. Okay. All right, so if you think back to where we started last week when we were talking about derivatives of surfaces, we started by saying, okay, we can see many tangent lines at a point to a surface. So we ended up just looking at really the slopes of two of those tangent lines, the one in the x direction and the one in the y direction, which has a lot of information. But it kind of feels a little bit unsatisfying. So what we're going to build up now is the idea of a tangent plane. And if you think of a surface, you can imagine that at any point there's one tangent plane. So that's the kind of unique thing that we're going to look at, that is the analogous thing to, in one variable, having the unique tangent line, except at weird places. So that's kind of where we're headed with this. And we are going to use our partial derivatives that we found with respect to x and y to help us build up this idea of a tangent plane and directional derivatives. So this now pulls together pretty much everything we did from the first week, which is vectors and planes and all that crazy stuff, and the stuff we did last week, which was starting to talk about directional derivatives. So it's quite a nice, you'll see why we had to do what we've done so far in the syllabus, because we use everything so far. All right, so the first thing that you might be thinking when we talked about finding the derivative with respect in the x and the y directions is, but what if I want to find my derivative in a different direction? Okay, what then? Well, now we're going to answer that. But first, we're going to introduce a combination, a kind of a vector, which combines our information from our partial derivatives. And this is called the gradient vector, and it's written with an upside down triangle. Depending on who you speak to and where they come from, this symbol, whoops, come on, what is happening here? Okay, this is not working. That symbol, it will be called del or nabla, and it's a vector differential operator. And we will talk about what that means in a moment. But first, let's look at how it's defined. So basically it looks a little weird, and this might make you feel a little bit twitchy, because it is a vector, because it's got a component in the I direction and it got a component in the j direction. But what it does is it only really gets applied to other functions and vectors. Now you might think, what is she talking about? But you've already met an operator before. You've met the operator d by dx. It's an instruction which says, if I apply this thing to a function, then it says take the derivative of that function. So the equivalent of d by dx when you're in a multivariate setting is this nabla, which says, okay, create this new vector which has the component in the I direction of the partial derivative with respect to x and the component in the y direction of the partial with respect to y. Okay. And initially it might be a little bit like, why would we do this? Well, we do this because it turns out to be the most sensible thing to do in developing the theory that we want to describe the things that we want. In practice, what does it look like? Well, you don't see a nabla just hanging around by itself. You see it operating on something. In the same way that you don't generally see a d by dx hanging around by itself, it's always attached to a function. So we apply our nabla to a function. What do we get? Well, we end up with the partial with respect to x in the I direction. So that's some function of x and y in the I direction, and a partial with respect to y in the y direction. Okay. And we're going to make a lot of use of del. And the thing that's kind of cool about it is this is a vector. I mean, it's a vector operation, it does stuff. So you're going to see that we don't only just apply it like this, we're going to treat it like a vector. So we're going to cross it with things, we're going to dot it with things. And by now you might be seeing, if you think back to the first lecture, I said we want to talk about Maxwell's equations. And they had like this weird del thing and crosses and stuff. Well, we are getting there. Okay, so here you go. What I would like you to do is take a moment to find, so I will say del f, and when I'm saying just apply del to a function, so find del f, evaluate it at the point x equals 1, y equals 2, and then take a moment to think about what on earth this thing means geometrically. All right, did I get my partials right? Okay, so then I put those together and we get that del f of xy is equal to my partial in the x direction and my partial y in j hat direction. Okay, and let's just evaluate it at a point. 2 is 2 times 1, which is 2. Plus. All right. What is this thing?
Is that the normal vector of the tangent plane at that point?
It is. Shall we draw a picture? So you're absolutely right. Well, I picked a nice easy function. What does f of xy equals x squared plus y squared look like in 3 dimensions? We're hearing a... Yeah? Okay, what is a...
A paraboloid?
It's a paraboloid. It's a happy paraboloid because it's like this as opposed to a sad paraboloid. Okay. All right. So we've got our paraboloid, and just wondering if I can. Let me see if I've got GeoGebra easily accessible here. 3D rough. Oh, I want 3D. Come on. x squared plus y squared.
You have to make it a function of y as well.
Blah, blah, blah. Okay, this is not going the way. Alright, let's not waste too much time on this. I'm just not having a good GeoGebra day. We will carry on visualizing this. Okay. So, alright. Think about, so what is this thing here? So let me draw a cross section of my parabola. Well, if this is a cross section in the x direction, then at some point that is giving me the slope of a tangent line. I would have a similar cross section doing something like that, and my df by dy would be giving me my slope like so. So if I think about combining those two together at a particular point, my drawing skills leave something to be desired. So we're looking at this point over here. I've got a slope like so, and presumably a slope like that. And if I combine them together, I'm getting a vector that is pointing... Is this a normal?
I would say that it is the vector that is parallel to the tangent plane. But that's my intuition.
Yeah, I think so as well. Like if you move in the 1-1 direction, right? Like a directional gradient, it goes exactly in this direction with the plane.
So this is not the normal.
The normal would be if you have the -1 in the z,
Yes.
because then it points
Yeah.
away.
So at the moment, what we've got is a vector that is pointing, so it's if we look down, so if we do a cross section, so we will have a cross section here. We have a vector that is essentially pointing, where is it pointing? I've completely lost my geometric intuition for this. That is very sad.
It's Monday for everyone. It's Monday for everyone.
It's very Monday today.
Doesn't the vector point at the direction that the function will move at the next point in x or y? I mean, isn't the direction of this vector where the function will move as a whole with respect to x and y? It's going to point out where this circle will be elongated if you look at it as a cross section.
I mean, the circle isn't going to be elongated.
Yes, my lingo is not. Yeah. At the next instant, where the circle is going to be a bit bigger.
Yes.
The direction of this vector will be radially away from the center in the way.
Is it wrong?
It will be in the direction of the biggest change, I think.
Yes, but for that point, because this is for the point 1, 2. So if we go to 1, 2, it has to increase more.
Well, if we go to the point 1, 2, so that
It's
we're
increase more from the j direction rather than the I direction, because we're more.
okay. Let's suppose that this is our x and our y, and this is our point 1, 2. Does that look reasonable? Okay. Then what does this thing look like? It is the vector that points 2 in the x and 4 like that, something like that, which is not making sense.
It makes.
But it makes sense because then it is the normal vector of the tangent line, right? It's just if you would take
Okay, because we're not seeing the
scalar product of this vector together with the actual tangent line, then you would get 0, so they're orthogonal to each other. Yeah, no.
Sorry, I'm just having a complete blank moment.
Line of the circle, right?
Yes,
at the point 1, 2.
Yep.
and this should be orthogonal to the vector we just draw.
Yep. Yeah.
So
I think I just did a really bad drawing.
Yeah, but it should be. I mean.
Yeah. Okay, so we would end up having our yeah.
So it is the normal vector.
Okay. All right. Sorry, folks. Lecturers screw up sometimes too. Okay. So we are finding the tangent vector. I mean, sorry.
The normal.
The normal to the tangent plane at that point.
Yeah, but why are we finding that?
Because it's going to be useful for us.
No, I mean, no, but why are we finding out by taking the partial derivatives in x and y and adding them? Why does that result in the? I just don't really understand why that results in like the normal vector to the tangent plane.
Let me see if I have. I think I might have a diagram.
Because last week we found the normal vector by cross multiplying both tangent vectors, right?
Yeah.
And
So why is this cross product equal to our partial derivatives?
Yeah, because now we're adding the derivative factors, but normally for the cross you would cross those derivative factors, right? If the tangent vectors, you cross them, you get the normal vector, but now we're adding them. Or is this just something different?
This is something a bit different.
Yeah, probably.
So I'm going to try and find a better diagram, which
Yeah,
I think
okay,
will
the
help.
whole vector would be, yeah.
Okay. For the moment, until I get my intuition for this back, let's take it as given that this is the del thing that we need. And we'll look and see what happens next, and hopefully my brain will come back online. I will maybe record a little lecture later to cover this better. All right. So, that was the idea of del, and we will come back to del a lot. But now let's think about if we want to find the rate of change in some direction other than with respect to x or y. How can we do this? So now we're going to talk about the directional derivative. And this is just to kind of link it to the ideas of derivatives that you found before. So to keep things easy, we're going to assume that u is the direction we're interested in, and we've got some unit vector. Okay, so vector of length 1. And we'd like to find how that function is changing, how our function changes if you change in one unit in the direction of u. So up to now we've been finding if you change in one direction with respect to x or with respect to y. Now we're just going in any old u. And would have helped if I'd put this fixture. Okay. So you could write this, you could play the same game that we played with finding partials with respect to x and y, with your little, like adding a little change in. So you could add a bit of a change. So you've got u and v are your components of your u vector. You could make a little change in the u direction and a little change in the v direction and see what happens. So you could build this up in exactly the same way we've done before, and take the limit as you let your little change go to 0. But perhaps a more useful way of thinking about it, weirdly enough, is you can create a dot product of your direction vector with your del. With this thing we discovered here. So with the gradient of the function. Okay, I'm going to suggest that we take a slightly early break so that I can reset and be more helpful. So let's take a 5-minute break. Come back at 1:45, and hopefully I will have figured this out and got my brain back online. All right.